Get back into our aerobic respiration where we were last time. To remind you, this is Tuesday. We have Thursday, and then Tuesday, and then the next Thursday is our exam. And then after that is spring break. So looking at the long game on this Tuesday, we should be able to review for the exam. So make sure that you have done sufficient preparation by then so that the review will be useful. We don't want to be looking at things for the first time on that day. And we should finish our material easily. We're actually in good shape. I don't know how. I don't know what I forgot to do because we missed a couple days for that snow, but we're right on pace, so that's fine. I mean, I'm not complaining, but maybe we'll introduce some new topic or something. But in any case, just keep that in mind. So we are 3 lectures away, including today, from the exam, and this will be, actually I think that day is the day midterms are due, which means that your second exam will probably not figure into your midterms, which I don't know that matters. I'm not sure why do the midterms matter?
They're just a progress report.
So like I can tell you what your grade is and how you're doing in the class, but the midterm will not probably reflect, well, I don't know, I might be able to get it done and put it in there. But this also assumes that your lab instructors will give me your test, and so far only one lab instructor has given me grades,
Wait, which one?
O'Keefe. But again, we've got a week, so hopefully, the boy can dream that I'll get their grades by then. But as I've told several other students, if you want to know how you're doing in the class, feel free to ask me. If you know your lab exam grade, you can tell me that. I can figure it into your grade, and I can give you the balance. But the midterm grades, depending on whether I get that exam on there or not, don't read too much into that. But hopefully you have a good idea of how you're doing just from knowing your grades. And I will post your exam grade, of course, before you leave for spring break. But then, for spring break, you don't have to worry about this class. There'll be nothing to study for or worry about until you get back. So hopefully you give your mind and body a break. All right, so let's back up a couple steps. Last time we got, I think, about halfway through respiration, which is good. So we're in good shape, as I said. Let's review what we've already done and what we know, and then we'll go back, or we'll start with some new material. So in respiration, a key thing to remember is that inside the cell, there are 2 places where aerobic respiration is taking place. Now remember, aerobic respiration is specifically respiration where oxygen is waiting at the end of all these reactions. If there's no oxygen in the cell, respiration doesn't get past the first stage, okay? And so your body has a way to make energy in the absence of oxygen for an emergency, but you can't last that long. So if you, for example, are involved in an athletic event or some type of exertion, you will use up the available oxygen in your tissues, in your muscles specifically, at some point. And at that point, your body doesn't just shut down, right? You don't just stop doing what you're doing, but your body does shift to anaerobic respiration. So it's going to keep making energy even despite the fact that you've used up your available oxygen. And the upside to that is you don't just collapse all of a sudden, but the downside to that is that you produce lactic acid as a result instead of the normal outcomes of going all the way through aerobic respiration. And so the production of lactic acid can cause discomfort and pain, and as I said, it's not sustainable forever. You can't just run for days, but your body does have a system to overcome that. All right, well, let's back up. Let's do what I said we were going to do. So in glycolysis, this is happening outside the mitochondria. So of the 4 stages, glycolysis, pyruvate breakdown, citric acid cycle, and oxidative phosphorylation, only one occurs outside of the mitochondria. Everything else is happening in the mitochondria, and that's really important because the membranes of the mitochondria are going to play a big role in how we generate energy. But the first stage, glycolysis, occurs outside of the mitochondria, and the purpose of glycolysis is to split that initial sugar in half, okay? And we're gonna get a little bit of energy from that, but not much, okay? We'll produce 4 ATP, but we invest 2, so we only end up, our net yield is only 2. Then, once we have split our 6-carbon sugar into 2 3-carbon molecules, which are called pyruvate. The pyruvate is transported into the matrix of the mitochondria. So it's going to go through both of these membranes and end up on the inside where pyruvate breakdown occurs. This is where we start to shed carbons. So in the first stage, we're splitting the molecule, but in the second stage, we're starting to pull carbons off and harvest electrons, which have energy. And when we pull those carbons off, they have to go somewhere. So every time you exhale, you're releasing carbons that you have broken off of organic molecules in the process of getting energy. So that CO2, as it leaves, takes the carbons with it. Now, we still have two carbon molecules, so we went from 6 to 2 sets of 3, and now we're at 2 sets of 2. And so those 2 carbon molecules are going to go into this thing called the citric acid cycle. We haven't talked about that yet, but we will today. The citric acid cycle is also going to shed carbons in the form of carbon dioxide, and it's going to generate a little bit of ATP, but not much, right? Only a couple, just like glycolysis. The important part of the citric acid cycle is the amount of electron carriers it makes. And to remind you, these electron carriers, NADH and FADH2, are molecules that are good at taking a high energy electron and then giving it away in a different place in the cell. Not many molecules can do that. So those electron carriers eventually give their electrons away during oxidative phosphorylation. And oxidative phosphorylation uses the high energy electrons to create a gradient, which is why we talked about membrane transport before this. They're going to create a gradient, and that gradient of protons, which are hydrogen ions, are going to want to come back across the mitochondrial membrane, and when they do, they're going to generate energy in the form of ATP. So it's quite a web we're weaving here. Oh, this will work better if I plug it.
Still learning how to work this thing we call computer. Nothing more in the dark.
There we go. Okay, so we summarized this last time, and again, you have all these slides, so hopefully you have all of this packed away. But the summary is to focus on where energy comes from, and where the electron carriers come from, and where the carbons leave. So we have energy at 3 different stages. The first 2 stages the first 2 stages where energy occurs, pretty low output. Okay, so a total of 4 ATP. And the reason this is only 1 ATP is that's per acetyl group, but we have 2 acetyls, so really it's 2 ATP. And then the mother load comes at the end when we cash in those high energy electrons. Along the way, all 6 carbons from that original glucose, if that's the energy source, remember we can get energy from proteins and lipids and other things as well, but we're just focused on glucose today. All those carbons from the glucose are shed as carbon dioxides. And then, the last thing, which I didn't circle here, is that these electron carriers that we're collecting along the way all get cashed in at the end for that large payoff. Okay, now this is something I'm going to hold you responsible for. It feels a lot like a quiz. It looks just like a quiz. All it lacks are numbers. It's foreshadowing. It means I'm going to give you a quiz that looks like that, if I can be any more clear. So that means it'd be a good idea to memorize this sheet. So I gave you a copy of that. I have another copy of that, which I'm going to give you today, and we're going to do a practice, but not yet. We don't want to, well, my PhD mentor, who is a close friend and a lifelong advisor, said one of my problems, he's not usually critical, but he did say, my problem is I peak too early. I prepare and prepare and prepare long before something is due. And that's not great. You should peak at just the right time. So when I peak too early, like if I prepared for a seminar in graduate school to make this presentation, and I prepare a week early, then by the time the seminar comes around, like all my energy's gone and I've forgotten a lot of what I've prepared. So he said, don't peak too early. So we're not peaking too early on this, but we are going to peak, and it's going to happen today. Okay, so let's start at the beginning. Glucose is broken down into 2 molecules, so it's split into 2 3-carbon pyruvates. Along the way, the NADH and ATP don't come directly from the glucose, but they're generated in this process. So electrons that have been stripped away from that sugar get added to the NADHs. Those are going to hold those high energy electrons. A little bit of ATP is made. Now remember, in this little family tree of respiration, whenever we have something on the next line, it can be traced back to a single molecule. So the pyruvates, not the NADH, not the ATP, the pyruvates generate the products for the second tier. And those products include the acetyl-CoAs, which are 2 carbon molecules attached to this long mega molecule called coenzyme A, the CO2s, and then more electrons are added to more NADHs. Okay, so the CO2 is you exhale that, the NADH is tucked away for later, but the acetyl-CoAs, these are gonna generate another generation of products. And so in this generation of products, we have, again, everything's in duplicate, so really you just have to memorize one side. More carbon dioxide, so the acetyl-CoA, the 2 carbons in the acetyl group leave. NADH collects more electrons, FADH2 collects some electrons, and then we have a little bit of ATP, right? Just 2 total. So at this point, we've only made 4 ATP. But then we cash in all of these NADHs from all of the levels, right? I don't have a good way to write that on there, but all of those NADHs are going to eventually yield ATP, all right? And the first is called what? What's the first stage called? Glycolysis. What's the second stage? Breakdown of pyruvate or pyruvate breakdown. Either one is good. Third stage? And the fourth stage? Okay. 8 of you are going to make at least 4 points on the quiz. That's good. That's 32 points total if the 8 of you carry through. So that we can celebrate that. Let's try to be positive on this gloomy, rainy day. Okay. So again, to review, the first stage was the glycolysis. We invest some energy. The reason we invest energy is you want to add phosphates to our sugar molecule. There are 2 reasons we're doing this. The first reason is that once the glucose comes in the cell, we immediately add a phosphate. I think I have a better version of that. Yes. We immediately add a phosphate so the glucose doesn't leave the cell. Remember, when glucose comes across the cell, it's coming across a membrane transporter, and it goes through this channel, which is designed specifically to import glucose. So if glucose becomes phosphorylated, excuse me, it can't leave out the door that it came in. And so that locks it in the cell. And then we add another phosphate, and the reason we add the second phosphate is now we have this high energy, double phosphorylated molecule, and if we shed those phosphates, we can make ATP, which is exactly what we do. So we have unstable phosphate bonds. Those phosphates are dying to break off. When they break off, ADP is waiting with open arms, right? And so they jump onto that ADP molecule, and we've got our first 2 ATP. Okay, the second stage, and this is where we ended last time, if memory serves me. I think so. The second stage then is the breakdown of pyruvate, and here's our 2 transporters. Remember, we talked about symport, which is when a transport molecule brings 2 molecules in the same direction across the membrane. And so this is bringing in protons. That's going to matter later, not so much right now. And it's bringing in the pyruvate, the 3 carbon molecule that was the result of the first stage glycolysis reactions. That pyruvate is going to be added to this beautiful molecule, coenzyme A, which is basically ATP, right? This molecule, everything I'm circling right now, if we moved that phosphate down here, up here, we would have ATP. So this is not a molecule we haven't seen before, it's just rearranged. So coenzyme A is added to the 3 carbon pyruvate. That's just a temporary arrangement. The coenzyme A is going to leave in the next stage. It's just there to carry acetyl-CoA into the citric acid cycle. And then there's our carbon dioxide. There's our electron carrier that got electrons when the bonds of the pyruvate were broken to release carbon dioxide. Those electrons in those covalent bonds had to go somewhere, and NADH sucked them up, and now it's going to hang on to those high energy electrons until the end.